Welcome to Semester 3, Mathematical Analysis. Today we are diving into a fascinating and powerful topic called uniform continuity. If you have ever wondered how mathematicians guarantee that a function behaves predictably across its entire domain without any sudden chaotic changes, you are in the right place. We will build this concept from the ground up, so let us get started. Now that we know our topic, let us build some intuition. Imagine you are driving a car on a winding mountain road. Standard continuity just means the road has no sudden gaps or cliffs. It is a single unbroken path. However, on this unbroken road, the turns might get sharper and sharper the further you drive, requiring you to spin the steering wheel infinitely fast to stay on track. Uniform continuity is a much stricter rule. It guarantees that the road never gets infinitely tricky to navigate. You do not need to constantly recalculate your safety margins at every single mile marker, because one global safety margin works for the whole journey. Let us translate that driving analogy into mathematics. In this formal statement, the symbol epsilon represents our chosen output tolerance, which is always a positive number. The symbol delta represents the universal input window that we must find. The letter D stands for the domain, and the variables x and y represent any two arbitrary points chosen from that domain. The formula states that if the horizontal distance between any two inputs is less than our universal delta, then the vertical distance between their corresponding outputs is guaranteed to be less than our chosen epsilon. Crucially, as epsilon decreases, the required delta will also decrease, but it will never depend on the specific locations of x and y. To really see what this formula means, let us look at a visual representation. The diagram you are seeing captures the essence of uniform continuity. Imagine the rectangular box, defined by a width of delta and a height of epsilon, sliding along the entire length of the curve. Because the function is uniformly continuous, the curve will never become so steep that it breaks through the top or bottom of this fixed size box. The exact same box works everywhere on the graph. This is critical in fields like computer science, where a programmer can set a single global step size for an algorithm and guarantee accuracy everywhere. While the sliding box is a great visual, proving uniform continuity directly from the complex definition can be algebraically exhausting. Fortunately, mathematicians use a stronger, easier-to-check condition called Lipschitz continuity. A function is Lipschitz continuous if there is a strict global speed limit on how fast it can change, represented by a constant number k. If you can prove that the steepness of the graph never exceeds this constant k anywhere, the function is guaranteed to be uniformly continuous. This gives us a highly practical tool for analyzing functions without getting bogged down in complex algebra. Let us look at the mathematical rule for this speed limit. In this formula, the left side represents the vertical distance between any two outputs on the graph. The right side represents the horizontal distance between the corresponding inputs, multiplied by our constant speed limit k. This inequality states that the vertical change is always less than or equal to k times the horizontal change. As the constant k increases, the function is allowed to be steeper. But as long as k is a fixed finite number, the function remains uniformly continuous. Finding the universal input window then becomes as simple as dividing your desired output tolerance epsilon by k. Now that we have our Lipschitz formula, let us see it in action with a concrete example. We are given the linear function f of x equals 3x plus 2, and our domain is the set of all real numbers from negative infinity to positive infinity. We need to prove this is uniformly continuous. We start by calculating the absolute difference between the function's outputs at any two arbitrary points, x and y. Substituting our function in, we get the absolute value of 3x plus 2 minus the quantity 3y plus 2. The positive 2 and negative 2 cancel out completely, leaving us with the absolute value of 3x minus 3y. Continuing from our simplified expression, we can now factor out the common multiplier. Because 3 is a positive constant, it can be pulled completely outside the absolute value signs, giving us 3 times the absolute value of x minus y. This final form perfectly matches the definition of Lipschitz continuity. The number 3 acts as our constant k, proving that the function slope never exceeds this value. Because we have proven the function is Lipschitz continuous with a constant of 3, it is automatically uniformly continuous. For any given output tolerance epsilon, we simply choose our universal input window delta to be epsilon divided by 3. This single choice guarantees our output stays within bounds everywhere. We just saw how to prove uniform continuity algebraically, but there is a powerful shortcut known as the Heine-Cantor theorem. This theorem states that if a function is continuous on a closed and bounded interval, written as a to b in square brackets, it is automatically uniformly continuous. Because the domain is just a finite stretch of the number line and does not go to infinity, the graph cannot become infinitely steep. The function is essentially trapped in a finite box. This means its rate of change is naturally capped, guaranteeing that a universal input tolerance will always exist without needing to calculate it globally. Let us apply the Heine-Cantor theorem to a new problem. We are given the quadratic function f of x equals x squared. Unlike the previous example, our domain is restricted to the closed and bounded interval from 0 to 5. We will prove this manually to see exactly how the bounded domain saves us. We begin by substituting our squaring function into the standard formula for the difference in outputs, giving us the absolute value of x squared minus y squared. Using the standard algebraic rule for the difference of two squares, we expand this into two distinct multiplying factors, the absolute value of x plus y times the absolute value of x minus y. This is the critical step where the bounded domain comes into play. We need to isolate the difference in inputs, but we have this extra variable factor of x plus y. Because both x and y are restricted to the interval between 0 and 5, the largest possible value for their sum occurs when both are exactly 5. Therefore, the first factor can never be larger than 10. By replacing the variable factor with its absolute maximum value of 10, we create an inequality. This shows that the output difference is strictly bounded by 10 times the input difference. If the domain went to infinity, this factor would also go to infinity, destroying uniform continuity. To conclude our bounded domain example, we have successfully transformed a variable rate of change into a strict global speed limit for this specific interval. We have shown that on the interval from 0 to 5, the function behaves with a Lipschitz constant of 10. Therefore, for any chosen output tolerance epsilon, we can set our universal input window delta to epsilon divided by 10. This perfectly illustrates the Heine-Cantor theorem in action. Because the domain was closed and bounded, the function's steepness was capped, guaranteeing uniform continuity. Let us summarize what we have learned today. Uniform continuity is a powerful global property that ensures a function's rate of change is manageable everywhere. By finding a single input tolerance that works across the entire domain, we guarantee predictable behavior without sudden chaotic shifts. We saw that this can be proven algebraically using Lipschitz continuity to find a global speed limit, or guaranteed conceptually by the Heine-Cantor theorem on closed and bounded intervals. Understanding this concept is a cornerstone of stable mathematical analysis, ensuring that both theoretical math and computer algorithms remain reliable. Great work today, and keep practicing these proofs.